Alright, this is our second example in the Gauss law chapter. We are now going to consider cylindrical symmetry. So we will use cylindrical symmetry in order to find the electric field inside a charged object that has the shape of a cylinder, and to find the electric field outside of an object that has the shape of a cylinder. Alright, so first, that question is not on the note, it's a general example. We will solve later on example with real value regarding cylindrical symmetry. What we want to do here is we have a real object drawn in black that has the shape of the cylinder, and it has a uniform volume charge density. In other words, the charge are spread evenly throughout the cylinder. All right? Now we want to find the electric field inside the cylinder, and we will use a technique similar to our example with spherical symmetry. What we will do is we will draw an imaginary construct called a Gaussian surface, and in this case it is a Gaussian cylinder inside or the object that has the shape of a cylinder. Now the reason why we can use Gauss law here is because the charges are evenly distributed, which means that the electric field at each point on the surface of the cylinder will be the same on the surface of the contour, by the way. Now, one thing we need to mention when we are applying Gauss law to a cylinder, this is an approximation, because in reality, there is some part of the electric field going to the both edge. But if we are considering a very long cylinder, let's say a wire, and we're considering an electric field inside the wire or near the surface of the wire, it is a really good approximation then, all right? So in our example, in this chapter, in the course itself, you can assume that the electric flux is only going through the contour of our cylinder, all right? That's important, and we'll see why in a moment. So we want to calculate the charge inside our Gaussian cylinder. To calculate the charge inside our Gaussian cylinder, we multiply the volume charge density. Again, this is a constant, it does not change. Multiply by the volume. Well, this is the volume of a cylinder, and the volume of the cylinder is pi r squared multiplied by the length of the cylinder. All right? Now, one part that confused many of my students is the length over here. It's not obvious, but it does not matter what length you decide to choose. It will cancel out later on in the formula, all right? So at first, many students are saying, well, what length should we take? Is there a set value for that one? No, there is not. And you will see it's cancel out, so don't worry with that part. The second thing is the area of our Gaussian cylinder, and again, we are considering only the contour. Okay, we don't care about the both end, all right? Only the contour of our cylinder. Well, the contour of our cylinder, to calculate the area, is the circumference multiplied by the length. 2 pi r multiplied by L. Now notice L and L, that's why they will cancel out. The area of the contour and the charge inside, both are dependent on the length, and they will both cancel out. All right, so let's calculate the electric field inside the cylinder. So E is equal to the charge inside. Now note, I've written Q in now, because it's not the first time I give this course. Every semester, the biggest mistake I think in the complete semester is not correctly identifying what I mean by the charge over here and by the area over here. The charge here is the charge inside our Gaussian surface. The area here is the area of our Gaussian surface. Always in Gauss law section, this is always the charge inside the Gaussian surface. This is always the area of our Gaussian surface. It never changes. These always represent the same thing, and believe me, this is the most common mistake probably in this semester, all right? So when we talk about the charge inside the Gaussian surface, we're talking about that charge here, and we use that formula to calculate that value. When we are talking about the area, we're using this value, and this is the area of our Gaussian surface. Now, we replace Qn and A by these two formula. We get that term, we simplify to that term, we get the volume charge density multiplied by the radius, or the distance from the central axis, divided by 2 epsilon 0. All right? Now let's consider the electric field outside of the cylinder. Now if we were to to consider an electric field outside, we will draw, it's a bit hard to not completely butcher my diagram over here, but we will draw a bigger Gaussian cylinder outside, and we will be considering now the electric field on the surface of that big cylinder. And again, we're going to use lowercase r to denote the radius or the distance from the center of the axis. Now note, I did not mention it, but our Gaussian cylinder has to have the same axis as our bigger cylinder. They have to be at the same center, basically. Otherwise, this does not work. All right, now we want to consider an electric field here. Well, now the charge change, because as you go farther and farther away from the center, there comes a point when you reach the surface of the real object. Beyond that point, you do not add any more charge. When you go from the center here to the surface of the real object, as you grow your Gaussian surface, you increase the amount of charge inside your surface. But once you reach the outer edge, you can grow your Gaussian surface as much as you want. There won't be any more charge. So to calculate, and I'm gonna write, I'm gonna write Q2, so it's the charge outside. In this case, will be the volume charge density multiplied by the volume of the cylinder, and it will be the cylinder, the real cylinder in this case. So it's pi r, capital R, multiplied by the L. Now notice it's the same L, it will cancel because we still, for the area, the formula did not change. It's only for this one, all right? Note that the capital R is the radius of the real object in this case, all right? So outside the cylinder, the only thing that changed in this formula is the Q inside the Gaussian surface. Now note, even though we are considering the charge of the real object, it is still the charge inside our Gaussian object. All right? So we replace Q with that formula, the area with this one. Again, we simplify, so we got volume charge density multiplied by r squared divided by 2, lowercase r, multiplied by epsilon 0. All right? So that's how you use Gauss law when there is cylindrical symmetry to solve the electric field inside the cylinder and outside the cylinder. Now note, I will be solving some example with numerical value, but you will see the principle is identical. It does not change, all right? So it's all about drawing a Gaussian surface, calculating the charge inside, and the area for Gaussian surface. The Gauss law section, really, it's all about Gaussian surface, charge inside the Gaussian surface, and the area for a Gaussian surface. That's it. All right, so see you in the next video. We're going to tackle planar symmetry now.